into. So let's see if we have any question yet. Okay, so if no question, let's move on. So we already discussed what is an instruction set. This is just to recap, just to do some quick review on it. So we say it's a set of instructions that the processor can again execute, and it defines the interface between the hardware and software, as we said earlier, and also the ISA specified operations that can be performed, the format of the instructions, the data type, and also the addressing mode, and also the number and the type of registers available to use, etc. So what is instruction set architecture? Also, this is we say the interface between the hardware processor and the software. The key role here is to govern the CPU design and machine level program. Yeah. So again, the first 3 or 4 slides is for recap of what we did previously. So this is our first 13.2 objective. So we shall go through the operation repertoire, the data types, the instruction, and most important, the addressing mode, more details, and also how memory is organized, or memory organization also. Wait for a few seconds if everything is okay. Good. So let's move on then. So first we start with the function of an instruction set. As we said earlier, again, instruction set perform the following functions. And we discussed this earlier, data processing, data storage, data movement. We talk about that also, and also control operation. So we won't go detail. For example, control operation, we talk about like branching on unconditional branching, like jumping, etc. Loops we can use, functions we can use. So let's go straight to the characteristics of instructions. And also we kind of mentioned all this, but we didn't really. So data transfer instructions, as we say, can be move, load, store. Arithmetic instructions also can be add, subtract, multiply, divide. Logical instruction can be AND or XOR, not. Branch instruction can be jump or call or return, etc. Then we have the input output instruction, then machine control, so instructions. Or let's wait for a few seconds if it's okay. So we also talk about operation code or opcode, which we say again specified operation to be performed. Then the source operand reference, we say it shows or indicate where the input data is located. Then the result will specify where to store the output or the result. The next instruction reference that would determine the next instruction to execute, often through the program count as we mentioned before. Yeah. Okay, this is the new now, this from here going. So first we're going to talk about different types of operands. So operands are data manipulated by instructions. In general, that's how we can put it also. So operand is the data operated upon by an instruction. Operands can take several forms depending on what the architecture, also the operation type we have. So we'll wait for a few seconds if any question. Okay, so let's go through. So we're going to talk about the common types of operand. The first one we're going to talk will be the address. Then we talk about numbers. Then we talk about characters. Then we talk about logical, okay, data. So let's start with the address first, which will be the next slide. So operand address. Here we can say that an address operand shows where data is located. At the address shows where the data is located. And this can refer to the, let's say, the register. So that would be a register addressing or memory location, the main memory location. This would be direct or indirect addressing when it comes to memory location. Or an immediate value also, value embedded in the instruction. So example given that we have a load R1 2000. This means what? We should load the content from the memory address 2000 and we put it into R1 register. R1. So let's move on. If no questions. So then next will be numbers. So numbers, as we all know, we have two types of numbers, a whole number or a decimal number. So when we talk about integers in a computer program, we always mean a whole number. When we talk about floating point numbers, we always mean it's a decimal number. Yeah, so those are the two types of numbers. And this can be represented in a binary form using the fixed bit length also. So I think that's the only language the computer understands. So both whole number and decimal number can be binary form. And also can be a sign or unsigned. When we say sign means it can be -10, they have a sign positive. Unsigned number means we don't care. And then normally, I think we discussed this already. In binary form, unsigned number, the first bit 0, positive then, or the first bit 1 will be negative. Then we talk about sign numbers. And normally sign representation, so we can use the two complements. The two complements as mentioned here, sign most significantly indicates sign two complements. Then we have the unsigned representation, all bits used for magnet. So unsigned representation means all the bits are for value or magnitude. There's no any bit for sign. Sign number means the first bit represent positive or negative, 0 or 1. So now let's go through the numbers. So we have the first one to be integer. So how, again, integer is represented. So we have the unsigned. All bit represent magnitude. And unsigned number means we don't have no negative value. The value start from 0. And we can see the range from 0 to 2 to the power n minus 1. So if it's binary, n is 2. Binary, the number of the maybe it can be 32, 64, etc. Now will tell us the range. Then we have the sign integers also, which means we use, as we said earlier, the first bit or the leftmost bit, which is first bit. 0 represent positive, then 1 represent negative. Then we have the two complements dominant method. Wait for a few seconds. If no question, let's move on. Then we have the floating point now. So with the floating point, we can see floating point use the IEEE 754 standard, which is the nearly universal standard. So we say floating point number is typically stored in 3 fields. We have the sign bit, the exponent, and matiza or significant. Significant. And M determine the precision, the number of decimal places. So I think precision will be the decimal places, something like that. No, not something like that, but that's it. So for example, in Java, we can say if it's a float, the precision is 7, so 7 decimal. Then if it's double, I think double, double, then it's 15 or 14, 15, something like that. Yeah. So we have a single precision, which is 32-bit, and we have a double precision, which is 64-bit. And it take up to 15 decimal places. Wait for a few seconds if any question. Let's keep going then. So the next will be characters. Characters here, we mentioned ASCII or ASCII or Unicode. These are very important. Even this is something as a programmer we don't want to know because operating system take care of everything. For example, if I have a character A, for the computer, it's not character A. It can be 67, it can be 66. If we convert it to ASCII or Unicode, also have different conventions, etc. So characters are represented by character code. Example would be the ASCII, typically stored in 8-bit bytes. So example will be A. Now it will be 01000001. Maybe it will be represent 61 decimal. If it's converted to decimal number system, we can convert it to know what decimal number is that. So the instruction will operate on as characters for string manipulation or again input and output handling. Wait for a few seconds if any question. Okay, so if no question, let's move on. So the next will be a logical data. So logical data, that's very quick one, 0 or 1, true or false. Some programming language such as Java, they use the word true or false. Now in the C language, or if I'm not mistaken, C++ also, one represent or 0 represent false, and any number represent true. Or sometimes we say 1 represent true, 0 represent false. So that's all we can talk about. And also the logical data, normally, anytime we have a decision, let's say the branching, that's conditional branching, or selection statement, let's say selection. Our output always will be true or false, only two, true or false, using the logical. So decision making conditional branches would be a good example for that. Okay, so if no question, let's move on. So next will be the operand. We have a composite data types. A composite data type means it's kind of like a data structure where we use a simple data type. Let's say, for example, a primitive type int with a character or string, and we can combine these two to create a data type name student. So when I create a student type, I have composite. I have both int for age and the name for the student name. But anytime I create let's say we use a record, or let's say struct in C++, use struct to create a struct named student. It's like I'm composite because you have more than one primitive type. Yeah, but again, here we say it's an optional. So some instruction set also support composite data types. Example will be arrays, which means you have more than one item. Records is the best example because when you create a record, you can create a record with 3 different primitive types. Let's say a record of student, name as a string or char array, if it's a C++, no C. Then we have age as a int. Then we have grade as a character. Keep going, it can be different. But anytime we create a student type, it's composite. It consists of all the 3 or 4 things we mentioned as one. Then we have to use the dot operator to assign. Well, yeah. So that's all we can say about the composite data. Can be common ones will be array, records, and strings. That's mentioned on the slides. And these data types are normally stored in a consecutive memory location and also accessed using pointers or the base address. The processor typically uses, we can use the loops or specialized instruction to manipulate these structures. Array, if you want to manipulate data in array, always we use a loop. Majority of the time, we use loop. For example, I want to add all the items in array. Most likely I'll use a loop to go through all of them. I want to initialize array. Most likely I'll use a loop to initialize all of them. So let's consider the instruction design or instruction set design consideration. So designers will consider all this. We mentioned again the simplicity versus performance, instruction length and encoding, number of operand. Instruction length can have effect on the system also, execution time. We mentioned before, number of operands, operand storage, register to memory trade-offs, and instruction type and addressing mode. As we said earlier, the address is too much. It's good, flexibility, but again, not too fast or not too simple comparing to small. Address length very small. So addressing mode normally will focus on the flexibility in accessing the data location. Instruction types also will ensure that the set support essential operations efficiently. Yeah. The last thing we can mention, a well-designed, again, a well-designed instruction set should simplify it. You should be able to simplify the compiler design, also improve execution speed. I think that's the most important, is simplicity and speed. And also reduce the hardware complexity, simplicity and speed. So that's all we can mention here, unless anyone have anything to add. If not that, let's see an example here. So example of number of addresses, I think we went through this already, kind of similar address. So as we say, if it's 3 address, we can have 3 registers and it's easy adding 2 items. If it's 2 address, then one have to behave like accumulator. I had R1 to R2 and I give this answer back to R1. So R1 become kind of measure, but one address is purely accumulator. A plus accumulator, the result back to the accumulator. So that will be the summary of this session. Here we say instruction set defines the operation, operand, and format. Also, characteristics, as we saw, include the data type, operation set, address, registers. Excuse me. Operand may be numbers, addresses, characters, etc. Yeah, the proper instruction design always improve the efficiency and hardware simplicity. Yeah. So that will be the conclusion here. So if no question, it's time for us to take our second break now. We are doing good. We have 54 minutes to go. So after break, we go to the third section, then we take our attendance. Or maybe, we'll see when we come back. So let's see if no question, I'm going to stop the recording.